Okay, this is a tutorial on the photoelectric effect. We're going to define photoelectric effect, look at the issues that came up when it was first discovered in the late 19th century, and then talk about the solution, both conceptually as well as mathematically. Also, we'll talk about a few applications for photoelectric effect in modern technology. So the photoelectric effect is a pretty straightforward idea. The name pretty much implies or tells you what's going on. Photo means light, electric means electrons. Essentially what you have is a surface, metals generally. Light comes in, hits the metal, rather than be absorbed and turn into thermal energy, it knocks an electron off. It ionizes electrons, and the electrons come off with a certain kinetic energy. So we have electrons knocked off of metal, and it's important it's metal when light or photons strikes its surface. All right, in of itself, this was not problematic. It's nothing more than a conservation of energy. Energy comes in from the light, from its intensity, and energy goes out in the form of kinetic energy of an electron. There's some energy that you have to overcome, by which the atom holds onto it, and so that's pretty straightforward. What was problematic was that certain types of light did nothing, whereas other lights did something that one didn't expect from classical theory. More specifically, red light. Okay, when you shone red light on the surface, let's say it was fairly dim, nothing happened. Then you made the red light brighter and brighter, and you'd expect eventually some electrons to come off it. Absolutely nothing happened, no matter how bright the light was. Okay, so for certain colors of light, no matter how bright, nothing happened, and your classic example is red. Okay. On the other hand, if you take blue light, you always get the photoelectric effect, no matter how bright or dim. Okay, so you could have a light source that was just firing one photon, or the dimmest light you can get, and boom, you get an electron. If you make the light brighter, you don't get more energetic electrons, which you'd expect classically, you just get more photons. Okay, so the intensity of the light had an effect, but it was simply the number of electrons as opposed to the energy at which they leave. In other words, their kinetic energy. So this needed an explanation because it was pretty straightforward to observe in the lab, but classical theory could do nothing to explain these odd results. So about 1905, Albert Einstein gives a very simple and elegant explanation. He essentially co-opts Planck's idea of light that Planck had used 5 years earlier to explain black body radiation. So Einstein said, look, treat light not as a classical wave, but coming in discrete quanta, these photons, and these photons each have an energy equal to hf. Now, right in here, it's h nu, the Greek letter, that's not a v. So light, or excuse me, red light, which is a low frequency, is going to have a low energy when it strikes the potassium. It's just not enough to ionize an electron, whereas violet or blue have higher frequencies, therefore are going to pack more punch when they hit the metal. Greater intensity simply means more photons. And even though you have more photons hitting it, you can't add up the cumulative energy of 2, 5, or 10 photons because they'd all have to be absorbed at the same time, and that's not going to happen. They're out of sync with, if you will, with how the atom vibrates. So the solution is, in order to knock off metal, you need to have a minimum amount of energy, and that translates to frequency, as we'll see in the equation later. Okay, in accordance with Planck's law. Anything less, doesn't matter how many you have, nothing's going to happen. So this ultimately explains why red light doesn't work, but blue does. Okay, very simple solution, and when we look at mathematically, it's equally straightforward. Okay, so the equation that Einstein gave us, and we're going to look at it in a few different ways, but the general equation, the way it's written, is we look at the kinetic energy of the electrons that are knocked off. Okay, so these are the electrons. Alright, and usually we're interested in the maximum value. That's going to equal the energy of the photon coming in. Alright, that makes sense. But we have to subtract off the amount of energy that the atom holds on to it. So that's minus phi, where phi is called the work function. Work function is the property of the metal, and it's essentially how tightly it holds on to the electrons. The bigger the work function, the more energy you need to knock it out the electron. Think of the work function like a hole. The deeper the hole, the more negative potential energy it has, and that's really what the work function is all about. Okay, so in this simple example, if we've got zinc as our metal in question, we have a 4 electron volt photon coming in, and we measure the electron coming off with 2 electron volts. We can ask, well, how tightly does the zinc hold on to that electron? In other words, the work function. And that's pretty straightforward. That's going to be simply the kinetic energy minus the energy of the photon. And if you subtract the two numbers, you get 1.5 electron volts. Then we can ask, all right, what is the minimum frequency you would need just to get the photoelectric effect? Not worrying about how much kinetic energy it has, just getting an electron to come off with a 0. So we can look at this graphically before we go to the mathematics. So let's say we have zinc, and this is represented, and we start off with a low frequency photon. There's going to be nothing happening, nothing. Then at some threshold frequency, F0, you're going to knock off an electron that has 0 kinetic energy, and thereafter it's going to rise as frequency rises. And it's going to rise linearly because we can see that the kinetic energy is proportional to the energy of the photon, and the energy of the photon, and I'm going to write the second form of the equation down here, can be written as HF according to Planck's law minus phi. Okay, so we see that KE is proportional to F. So we can say that the minimum, and when it has 0 energy, okay, that's going to mean that our energy of our photon equals the work function. So in this case, the minimum energy needed is equal to, so if we have E equals HF, all right, we can then say F equals the minimum energy, which is the work function, 1.5 eV, divided by Planck's constant. Now, normally we'd use 6.6 times 10 to the negative 34 joule seconds, but since we're in electron volts, we're going to use the other value of Planck's constant, 4.14 times 10 to the negative 15th eV seconds, and if we plug those numbers in our calculator, we should get about 3.9 times 10 to the 14th hertz. Okay, so that's right about square in the violet blue part of the spectrum. So if you shine red light or orange light on zinc, you are going to be below this threshold frequency. Nothing's going to happen. If you shine violet or ultraviolet, you're going to be up here and it rises steadily. Where the slope of this, according to this equation, would be Planck's constant because F is our x variable. And then if we want to extend our line backwards, right, then where it intercepts the y-axis, that would be the work function. And then when the work function, when we're at the threshold frequency, the work function, we have 0 kinetic energy, then we can say that the work function is equal to HF0. So we can also write this equation as HF minus HF0. So we have 1, 2, 3 ways of looking at the kinetic energy, maximum kinetic energy of a photon when it's ejected. All right, what happens if a higher frequency photon shines on a zinc? That's pretty straightforward. Higher frequency gives you greater kinetic energy of the photoelectrons. Okay, so we give those electrons a special name, even though all electrons are identical. As a result, consequence of the photoelectric effect. And the last question we can ask is, what if we shine that light onto a work function or higher? What if metal has a higher phi? Okay, so conceptually it's pretty straightforward. We're going to have less kinetic energy, but what would it look like on our graph? So if we switch colors, well, again, we're going to have nothing until we get to the threshold frequency. But since we're at a higher threshold frequency phi here, we expect that to happen at a higher frequency. So let's say the photoelectric effect occurs here, and then thereafter it's going to go up steadily, and this line should be parallel to that line. So we get exactly the same graph, it's just shifted to the right. So we have the same slope, in other words, Planck's constant, h, shifted to the right, which would correspond to a higher phi, because if we extend this all the way back to the x-axis, we see that we're in a deeper hole, which corresponds to a higher work function. All right, so the last aspect that we want to discuss here is a subtle thing, and that's more on the experimental side of things. We've been talking about the kinetic energy of the ejected electrons. So the question is, how do we know what the kinetic energy is? When you're first measuring the photoelectric effect, how do you know that blue light gave a higher kinetic energy than, let's say, green light? Well, it all has to do with the circuit that can be set up using the photoelectric effect. So here is our phototube. Right? It's essentially a glass with a vacuum in the inside, and you have two plates, with the idea that when light comes in and strikes a plate, it knocks electrons off from the anode to the cathode. And those electrons have a certain kinetic energy. If you've got a lot of light, then you get a lot of electrons, and you'll get a lot of current, or a relatively large amount of current. We're still talking nanoamps, microamps, etc. So what the idea is to figure out the amount of energy that these electrons have is to put an opposing electric field across here, so that the electrons, if you will, have to climb uphill. And the hill they have to climb is simply equal to the amount of voltage we put across here multiplied by their charge. So what you do is you set up a circuit where you put a variable voltage source that is in opposition to what the electrons want to do. In other words, the voltage source here, if you follow the negative, this would be a negative side, this would be a positive side, and the negatives are fighting this electric field. Okay, so we summarize it here in the 4 bullets. You have the photoelectrons move towards the cathode, and the ammeter measures the photocurrent. Okay, you place a variable voltage source in the circuit to oppose the flow of the electrons, so that's why we have a negative here and a positive here due to this variable voltage source. And then you keep turning it up and up until no more electrons can reach there. And you'll know no more electrons can reach here when the ammeter goes to 0. Okay, so you need a sensitive ammeter. And then you can say that the opposing potential must equal the maximum kinetic energy. And that opposing potential is nothing more than a charge of an electron multiplied by the voltage that you set up by the variable voltage. So we see that equation, work done in an electric field is Q times V. So if we look at our original graph where we have KE and we have frequency and we saw something like this, we can now look at that in a similar fashion where you have QV and F, because these two are essentially the same thing. But very often you don't worry about the Q because that's just a given, so we usually plot stopping potential versus frequency. It'll be the same looking graph except that the slope will not be Planck's constant, but rather it will be Planck's constant divided by the charge of an electron. So be aware of that, where you can have essentially the same looking graphs, but you can have different axes, so your slopes will take on different values. Alright, so before we conclude our discussion on photoelectric effect, I'll talk about some applications. There are many of them, but the classic application is, if you will, a light sensor. Think of the doors that open in front of stores. You step on a mat and the door magically opens. There's a classic Saturday Night Live skit where the mat seems to be the thing that's key. What you're really doing is when you step in front of the door, there's a beam of light going across the door, and there's a photoelectric effect that's keeping a circuit going. So when you trip the beam, it turns off the photocurrent, which then you have a voltage divider in there, which will either make the door open or close, depending on how you have it set up. Same thing in your garage door openers. There's a safety mechanism that if somebody's blocking the beam of light when the garage door is going down, it won't close. Okay, using nothing more than light tripping electrons to set off a circuit. Okay, so this concludes our discussion on photoelectric effect.